Okay, so are you able to see the blank screen?
Yes.
Yes,
Okay.
sir.
Okay, I have one question before I start. What is the profile of the participant? That means how many master students, how many roughly, how many research students, and how many post PhD roughly?
Yes, it is a heterogeneous group.
Okay, okay,
Master students, researchers, and teachers also there.
okay. So not one group is majority, all together.
Yes, sir.
Okay, that is fine. Yeah. So I will not assume. I'll assume, of course, the linear algebra background to some extent, but otherwise it is self-contained. Okay, so I'm very happy to be present. I thank Jaidev Sarkar for the very difficult organization, because people feel that or online is easy to organize, which is not at all true. Okay, so he has taken a lot of trouble, and his team also. So I thank all of you for the organization. Okay, so my topic is Perron-Frobenius theory and matrices and graphs and so on. So I think today I'm going to just spend time first in the beginning on the basics of eigenvalues and eigenvectors and some facts which are not commonly known or are not that well known, I would say. And then I will move on to the non-negative matrices and graphs. So just to give some background, so some introduction to the whole series of 4 talks. So what is a non-negative matrix? So non-negative matrix is a matrix in which all the elements are non-negative, entry-wise non-negative. So we have to be clear about the terminology, because in mathematics, pure mathematics, non-negative sometimes means non-negative definite. But again, there is some confusion that non-negative definite is usually called positive semi-definite. But that is not what we have in mind. So a non-negative matrix is a matrix in which all the entries are non-negative. And usually we will consider a square matrix, although rectangular matrix can also be non-negative. And this theory of non-negative matrices, now it is also known as Perron-Frobenius theory, in honor of 2 great mathematicians who laid the foundations. I'll make some historical remarks later on, but that started the area. And somehow it is not, it has not come in the mainstream of curriculum, because the curriculum is usually geared towards higher courses in pure mathematics and functional analysis. So usually we switch on quickly to operators, and matrices are given not that much scope in the curriculum, like determinants, rank. They're not given that much scope, but those are very attractive topics, and now they are becoming important also for applications. So although non-negative matrices or Perron-Frobenius theory has remained in the background, the theory is quite it's very easy to understand and learn the theory, although it's not at all easy, I would say. The beginning parts are quite easy, but later on it gets quite complicated. But it's nothing beyond the scope of senior undergraduate or first year graduate students. So we will see some introduction to that, and simultaneously graph theory is also coming into play in a big way. So graph theory by itself is again a very big topic, which is getting attention recently. Recently means last 30-40 years, because of applications in computer science mainly. But the interaction between matrices and graphs is also quite fascinating. So that some of that we will see in this relationship between non-negative matrices and graphs. Because, yeah, a question? Okay. So when we talk of non-negative matrix, the entries can be positive or 0. And you may think it is not very important, 0 or non-zero or 0 or positive. But later on, we will see that zeros and non-zeros, their placement becomes very important. And so usually we can treat it as a pattern of, or you can say a 0, 1 matrix, where the position of the zeros is very crucial. And that is where the theory gets much deeper. So first we will talk about positive matrices. That means all the elements are strictly positive, and get the basics of Perron-Frobenius, or that is called Perron's theorem usually. And then we will move on to matrices where zeros are present. So, let me give you some background right in the beginning. So this was proved by the theory was started by Perron around in 1905, 1906. And interestingly, Perron did number theory also mainly, and he had some interest in continued fractions. He has work in continued fractions, and that is where he got interested, and he proved the Perron-Frobenius theorem. Actually, the initial proof is not available. I have not seen that proof even, so I really don't know what is the exact relationship with continued fractions. That is a topic for somebody who is interested in history of mathematics. But that proof is not available. I have not seen that proof. But that was the first proof around 1905. And then several people, so the basic assertion of Perron's theorem that you can remember, you may not remember all the other statements or the proofs, but if you take an entry-wise positive matrix, then among the eigenvalues, there is one eigenvalue which is positive. And that is the main assertion. And corresponding to that eigenvalue, there is an eigenvector which is also entry-wise positive. So that is the main theorem. And then there are some further properties of that eigenvalue and about the eigenvector. And then it gets much, much subtle. But at least this assertion itself is useful in applications many times. And so that is the basic assertion. And later on, so I think I'll just demonstrate, even for a simple situation like a 2 by 2 matrix, because we never think of it that way, that if you take a 2 by 2 matrix, which is positive, and let us talk about the eigenvalues of that. So here A, B, C, D are all positive. And as you know, the eigenvalue, so the trace is positive. And as you know, if one eigenvalue is complex, the other eigenvalue has to be complex. And so if we show that there is no complex eigenvalue, then both the eigenvalues are real. And because the trace is positive, one eigenvalue must be positive. So that is the assertion. So all we have to do is to show that there is no complex eigenvalue. And we will just use our very, very simple high school mathematics that calculate the characteristic polynomial and then use the discriminant to determine when are the roots. So this is non-negative, roots real. So this is the characteristic polynomial determinant of this. And that if you simplify, it comes to lambda squared minus a plus d. Please correct me if I make some mistake, because it's always possible that there are errors. So this is the characteristic polynomial. We will talk more about the properties when I talk today about further about eigenvalues. And then all we have to show is that this has no complex root. So we will calculate the discriminant, b squared minus 4ac. So a plus d squared.
So there is a plus AD.
D minus B.
Okay.
So plus AD.
No. Where? Oh, here?
1 plus AD, just AD. This
Okay,
term.
at the
A
end.
times, A
Okay,
times.
okay. Plus AD. Right. Thank you. Okay, so we will just calculate the discriminant. And so you get b squared minus 4. Okay, so okay. And then try to show that the discriminant is positive. So you get a squared plus 2ad plus d squared minus 4bc.
Hello, sir.
Yeah, there's some mistake. Yeah.
There should be AD minus BC.
Okay, then I can make here positive.
Yes.
No, but it okay. So inside now.
Yes, sir. Fine.
Okay. So a squared plus 2ad plus d squared plus 4bc minus 4ad. Okay, so that is a squared minus 2ad plus d squared plus 4bc. And so this is a minus d squared plus 4bc. Now you see where the non-negative, so far the non-negativity has not played any role, or actually I'm assuming they're positive right now. Even non-negative will work. But because of that, now you know that this first term is definitely non-negative. And the second term, because B and C are non-negative, the second term is non-negative. So you can see that the non-negativity plays a very important role here. And you may not have seen anything like this in your linear algebra course because this is not covered. People are not paying attention to these sign properties. But because of non-negativity, 4bc is non-negative, and so the discriminant is non-negative. So we can say that the roots are real, and then one of them must be positive. This tells you something more, that I never use that B and A and D are non-negative. And if you think about it, that is not required, because if you take we can always change the diagonal by some constant. You must have seen it in some exercises that if you have a square matrix and if you add a scalar matrix, that means a constant times a diagonal, then the eigenvalues only shift. They don't change. So if you have a matrix, even say a 2 by 2 matrix, where these two elements are positive or non-negative, and these two elements are arbitrary, I can always add a big delta times I, where delta is sufficiently large, that will make it positive. And then if the eigenvalues of this matrix and the first matrix, they are only shift by delta, they differ only by delta. So it is sufficient to show that this new matrix has a real eigenvalue, and so the diagonals don't play a very important role. That means this is sometimes called essentially non-negative. That means all the entries are non-negative except possibly the diagonal. And later I'll talk about it. There is a whole class of matrices called M matrices, M for Minkowski, which is essentially non-negative matrices in disguise, because you just perturb the diagonal, and so that the big theory of M matrices. And although we will not go into details of M matrices, that is essentially part of Perron-Frobenius theory. Okay, so this demonstration shows, now if you go to a 3 by, but this also tells you that if BC is positive, the product, if the product BC is positive, then that is sufficient. So B and C can both be negative also. Still, it will have a real eigenvalue. Okay, so this was just to show that even for a 2 by 2 matrix, there's something to learn about the eigenvalues. Okay, when you go to a higher order, of course, you need other proof techniques. This technique is not going to be enough. Okay, now I'm going to erase this screen, and unfortunately, I cannot recall the screens because when I erase it, it is gone. So if you want to ask something, you can make a note of it, and later on you can recall. I'll do my best to sort of recall. But if you have any question, you can ask right now or later on. Yeah. Any question?
No,
Okay. Is there a question? Okay, so I'm going to erase this.
Sir,
Yeah.
if the diagonal entries are arbitrary, you mean it should be real or complex?
No, if the diagonal elements are arbitrary, but the off diagonal elements are positive, suppose, then eigenvalues are real. Because the same
If the
proof.
diagonal entries are complex, then also it
No,
will
no,
be
no, 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 no. Real.
Okay.
Real. So in this series of lectures, we will always talk about real matrix, but we have to talk about complex numbers because of eigenvalues. But very soon it will be gone. So complex numbers, you need not worry too much except in the beginning. So yeah. So all the elements have to be real and in fact positive here, but the diagonals can be arbitrary.
Sir?
Yeah.
Sir, so even if they're complex, the same thing should work.
No, I'm not sure whether the
Because we are adding anyway, so we can subtract that part in the
no,
the
no,
inductive part.
I'm not very sure because this inequality kind of thing. This how will you talk about
No,
this?
when we are adding delta times identity, that time we can adjust the complexity. So only if the diagonals are complex.
You mean you want to if there is I, you want to add minus I?
Something like that.
No, but then the eigenvalue shift by I, so I cannot go back and talk about the original matrix. Okay, very easily. So there is some problem with complex. So anyway, think about it. I'm not taught much, but I think that is not going to solve the problem. So any other question? Or if this question is not clear, you can ask again. So this is one comment I have about linear algebra courses that we learn. When you learn vector spaces, determinant, rank, linear equations, as you know, all this can be done over a general field. Not much problem will come. And very often it is interesting how the proofs will go over if you don't have real or complex. Like we all know that rank of AB or rank of A plus B or rank of AB is less than or equal to rank A and rank B. That we have all learned. But the proof that we learn is over a field. But suppose I have a matrix over a commutative ring. I have to have commutative because determinant has to be there. Then if you have a commutative ring, then we can always talk about rank through determinants. And then this inequality is valid. But the proof, the usual proof doesn't work. And one has to resort to Cauchy-Binet formula or some such thing. But proofs get very interesting. Most of the rank inequalities, they are valid over matrices over rings also, commutative rings. So the linear algebra that we are doing in the beginning, up to eigenvalues, that is valid over much more general structures. So you can take, for example, integers modulo 6, which is not at all a field, but you can do most of linear algebra, rank, linear equations, consistency, determinant. But students are not toward that. I think that is unfortunate because you have a much richer theory which is already proved, essentially, or not proved, but at least stated. And like something is true in a much broader structure, you should be aware of that. But when you come to eigenvalue, the whole thing changes because eigenvalue, we have a characteristic polynomial and we are going to talk about its roots. And then the fundamental theorem of algebra has to be there. And so there, I think the complex field is required. Okay, so for the full glory of linear algebra, complex field is necessary, but for most part, you can do it over real field. And especially, okay, I think let me now start talking about eigenvalue, the basics, and then make more comments about these eigenvalues and eigenvalues. Okay, yeah, so I was telling you about the other proofs of Perron-Frobenius theorem. So there are several proofs. So Putnam and Carlin, they gave some using analytic functions. So I think it's a good project if some student interested in mathematics collects all these. They are not collected. Nobody has collected because some of them are quite technical. especially as I made a remark, original proof of Perron, I don't even know whether it's available properly. But one thing is certain, that it uses continued fractions, or it talks about continued fractions. So Putnam and Carlin gave a proof using power series, complex power series. Then Ostrovsky, these are all big names, okay, mathematicians. Ostrovsky and Householder, they use norms, matrix norms, to prove some Perron-Frobenius theorem. Then Wieland and gave a proof. Then Blackwell gave a proof using the minimax theorem of von Neumann, and that will be a little bit closer to what we are going to do. And so that is the history. And then the extension to non-negative matrices. That means, as I said, the zeros play a very important role. So the initial theory is about positive matrices, all the elements positive. But then the Frobenius came into play, and in 1912, he gave a proof when he extended the theorem when zeros are present. And Frobenius is a very important linear algebraist, student of Schur, who is himself a great linear algebraist. And Frobenius developed the whole theory of minimal polynomials and roots of minimal polynomial, as we know, and as we learn in textbooks today. And he developed the theory of Perron theory for non-negative matrices, and which we will see, parts of that we will see, although some of them without proof, because the work of Frobenius is very difficult. Very difficult means very deep. One can read it and sort of enjoy it and understand it. It's not that it is beyond reach, but it cannot be simplified. It's very solid piece of work. So Frobenius' work on irreducibility and reducibility, which we will define, and he showed that all of this Perron's theorem is extendable to matrices which are irreducible. That means zeros can be present in a certain way, in a certain structured way, and then these results can be generalized. Okay, so this will be the subject of. So today I talk about eigenvalues, eigenvector basics, and I may even touch upon the first proof of Perron's theorem, that means positive matrices. Then I will move on to, in the next one, maybe tomorrow or maybe later today, to matrices and graphs. So relation with graph associated with a matrix and how that plays a role. And then we will talk about some more involved topics on reducible matrices like primitivity, index of primitivity, and power positive. And these will be mostly without proof. I'll state the results. And then I have some plan to talk about another structure, algebraic structure, where many of these results hold true. And that is a recent area, relatively recent area called matrices over max algebra. So that may be the last talk. It is good to know at least the basics of that new area, which is again highly developed now. And a lot of Perron-Frobenius theory in a certain way is valid over max algebra. Okay, so coming back to eigenvalues and eigenvectors. So now let us talk about complex matrix for a while. And so if you have a complex matrix, then there are two ways essentially you can define eigenvalues. One is that if A is a square complex, real or complex matrix, let's say, then I set up the equation Ax equal to lambda x, and where the important condition is that x is not equal to 0. And any lambda that satisfies this equation is called an eigenvalue of A. And x is called a corresponding eigenvector. Now, first question is why eigenvalue should exist. It is not immediately clear because this is not a simple linear equation. You cannot talk about consistency and so on because x is coming on both sides. The variables are coming on both sides. So we have to rearrange, then it becomes a linear equation. One more complication is that parameter lambda is there. And so we will show the existence. And that is one way to define eigenvalue, but the equivalent. So let me rearrange this equation. And you are familiar with all this, but maybe just recall that we rearrange this equation. And then we resort to the elementary linear algebra that this has a non-zero solution if and only if lambda I minus a is singular. And so I can define an eigenvalue as also a scalar lambda for which lambda I minus a is singular. And then that is equivalent to showing that the determinant of, or demanding the determinant of lambda I minus a is 0. And this looks like a different definition, but because of the basic linear algebra, they're equivalent. So these are the two definitions. And we will talk about existence. So existence of eigenvalue, as you can see from this determinant definition, that if you expand it, you get what is called a characteristic polynomial. And the first term, it is a monic polynomial. So lambda n to the power a, and then, so we will talk about these coefficients in more detail. And a constant term is determinant a with an appropriate sign depending on whether n is even or odd. And it becomes, this is called a characteristic equation, and the left hand side is the characteristic polynomial. And then we resort to the fundamental theorem of algebra that any polynomial with complex coefficients has n roots, degree n, then it has n roots. Roots may not be distinct, but those are called the eigenvalues, and they exist because of the fundamental theorem of algebra. And then how many roots, multiplicity, so we will talk about that. These things are not very well known, maybe in the usual course on linear algebra. So that's why I want to go over some of those things. Okay, here also there is one interesting thing, that when students look at this polynomial, so when you write the characteristic matrix, so suppose the teacher is introducing this determinant, then the students can rightfully say that, sir, we are not told how to solve this determinant. So the teacher says, why? The student says, because the lambda is present and we don't know anything about lambda. We don't know even whether it commutes with real numbers. Whether 2 lambda is lambda times 2, we don't know that. So this is called a lambda matrix actually. In literature, this is called a lambda matrix. And again, the teacher should tell the students, but the teachers themselves are not told this, so they don't know. They should tell the student that this is a new kind of matrix. It's a lambda matrix, and it is the first example you are learning about a matrix over something which is not a field. It is maybe the complex numbers together with an indeterminate lambda. But we will sort of close our eyes and assume that lambda commutes with all the scalars. And if lambda doesn't commute, you cannot simplify the determinant. You will get stuck at some point. And we will also close our eyes and assume that all the usual properties of determinant are valid. That means if 2 rows are interchanged, the determinant changes sign. Again, the same student who had objected earlier will say that, sir, how do you know that? We have never learned this with a lambda matrix. We have learned with a complex matrix. Now suddenly you are telling something which is without proof. Okay, so these are subtle points, and I think one should be aware of those points, that you are getting to see lambda matrix for the first time without realizing it. Okay, so we assume that all the usual properties of determinant are valid. We just go ahead and be bold in a way and simplify this determinant, and there is no problem. And we calculate the roots. and those are the eigenvalues. Okay, so we have got any complex matrix has n eigenvalues, but there may be multiplicities, and I'll talk about that. Okay, now coming to eigenvectors, as you can see that the eigenvector, there are a lot of eigenvectors for the same eigenvalue, because if x and y are eigenvectors, then obviously x plus y is an eigenvector just by adding those equations, and scalar times x is an eigenvector. And so it's almost a vector space, except that 0 is not there. So if we just add 0 also, that means if you define this space X such that Ax is equal to lambda x, including 0. 0 is not an eigenvector, but I'm including in this space, then it becomes a vector space. And that is called the eigenspace associated with the eigenvalue lambda. And like if you take the identity matrix, this space is very rich. It is the complete space. Every vector is an eigenvector. And eigenvalue, there's only one eigenvalue, that is equal to 1. Okay, so vector spaces are kind of large objects, and we will see the properties of that. Okay, so I'm not going to the eigenvalues, eigenvectors, they have applications, but it is not easy. So they are applied in various areas, most of the engineering mathematics or computational mathematics.
Sir, so when we talk about eigenspace, do
Yeah.
we already include x equal to 0?
Yeah. 0 is part of the eigenspace, but it is not an eigenvector. Okay. Because otherwise it is not a vector space. So we have to include that.
Okay.
Okay, so I'm not talking about the application. They're applied in many engineering topics and so on. And now eigenvalues. So some of the properties, like the invertible matrix, there are many equivalent definitions: full rank, full row rank, full column rank. All those 8 or 10 very basic definitions are there. Similarly, here we can use that. For example, A and A transpose have the same eigenvalues. That is not clear from unless you talk about the left eigenvector, because I have talked about Ax equal to lambda x, but why not take a multiply on the left? That means y transpose A is equal to lambda y transpose. So if you have a vector y which satisfies this equation, I'll use the dash for transpose, sometimes t also. Okay, so if it satisfies this equation, then also lambda is an eigenvalue, but then y is called a left eigenvector and x is called a right eigenvector. And right eigenvector, left eigenvector, there are some properties. But
Hello.
yeah.
Sir, the matrix lambda I minus A.
Yeah.
Is called lambda matrix. So
Yeah.
if we call it lambda matrix, then how do we know that this lambda is commutative or not? The confusion is as it is now.
No, I'm not talking about the Penrose theorem right now. I'm just introducing general eigenvalues. There's no positivity, negativity right now. Okay.
Not positivity. I am talking
A is a complex matrix. That's all. What was your question? That how do you know it is positive?
commutative. Lambda is commutative or not?
Lambda is?
Commute with numbers.
No, can you say that again?
Hello.
Yeah.
Sir, you told us that the matrix lambda I minus A is called lambda matrix.
Yeah. It is a lambda matrix.
And when it is a lambda matrix, then our lambda will commute with numbers. So
No, lambda in the lambda matrix, lambda is a variable. It is just a variable. Okay, it's an indeterminate. So when we calculate the determinant, it's a polynomial. It's not a number. For a particular value of lambda, it will be a number. You can substitute lambda and get the number, but in general, it's a variable or indeterminate, you can say. We don't know it is a number. This is not a number. What is the problem? Lambda is kept as a variable.
So, sir, how do we know that this indeterminate will commute with numbers or not?
Yeah, so I'm assuming that we will assume that lambda commutes with numbers. That we can assume because there are some properties of lambda. And if you assume that, that is the basic assumption we are making. And if you
So
make
with
that,
this
yeah,
sorry. So
then
with this assumption, we call lambda minus A is a lambda matrix.
no, lambda matrix is a matrix where the elements are complex numbers and lambda. That's a lambda matrix. But when we assume that lambda is commuting with the numbers, then we can calculate the determinant.
Okay. Thank you.
Yeah, so using that, now I can I claim that A and A transpose, if lambda is an eigenvalue of A, then it is also an eigenvalue of A transpose. Now that is not immediate from the first definition, but it is clear from this definition because determinant of A and determinant of A transpose are the same, and so A transpose will also have the same characteristic polynomial, and from there it is obvious. So some of the basic properties you have to know, you have to use both the definitions. Okay, so A and A transpose will have the same eigenvalues. Okay, now I have already shown that every matrix has an eigenvalue by this fundamental theorem of algebra. Let us look at one more sort of argument to show the same thing. One more proof. So if you have and this is where the minimal polynomial and so on are related to what I'm saying now. So if you take a polynomial with complex coefficients, suppose P in a variable, complex variable Z, suppose it's a degree K polynomial, Ck Z to the K plus Ck minus 1 and so on, and plus C1Z plus C0, where C1, C2, Ck are complex, then I can evaluate this polynomial at a matrix, at a square matrix. So suppose you have a square matrix A, then I can just substitute A to the powers. The only thing is when you come to the constant term, you have to put identity. That is the convention. So this becomes a matrix polynomial. So it's a matrix. And there's a theory of matrix polynomials also. We will not go into that. But if PA is 0, so we will be interested in polynomials such that PA is 0. And then P is called an annihilating polynomial. And this is the starting point of Frobenius theory of minimal polynomials and so on. So this is an annihilating polynomial. And why does annihilating polynomial exist? So again, this is a interesting application of elementary vector space theory and the idea of looking at a matrix as a vector. So if you have a matrix, you can always think of it as a long vector. So you have a matrix here. So I can just take the first column and then the second column. So I can convert it into a vector. So if you take a matrix A, think of that as a long vector of, if A is n by n, this vector will have size n squared. So it's a complex vector. And if you look at A squared, a cube, and so on, and also identity, that is something like a to the power 0, then you get a sequence of matrices, and because they are essentially vectors of size n squared, they cannot all be linearly independent. So I am talking of linear independence in the usual sense. That means thinking of them as vectors, I am going to vector space theory, basic vector space facts, and then they will become linearly dependent. In fact, because there are n squared vectors, as soon as you go to a to the power n squared, then because identity is also there, then you have n squared plus 1 vectors, and so they must be linearly dependent. And so there's a linear combination which is equal to 0. So if you take up to, I mean, if you want, you can go even beyond, but there's no need. If you go up to a to the power n squared, then there's a linear combination which is equal to 0. And so that means you get an annihilating polynomial. So existence of annihilating polynomial is proved by elementary vector space theory. Of course, later on we will see that you don't need n squared. Actually, n is enough. But existence of annihilating polynomial is guaranteed. And then another fact is that if you take an annihilating polynomial, then you look at the roots. So suppose P is an annihilating polynomial, then look at the corresponding polynomial Pz and take any root of Pz, the individual complex root. So suppose lambda naught is a root of this annihilating polynomial, then I claim that lambda naught is an eigenvalue of A. So let me repeat. Any root of the annihilating polynomial. So annihilating polynomial is a usual polynomial, not a matrix polynomial. It's a polynomial with complex coefficients. So any root of the annihilating polynomial is an eigenvalue of A. And that gives us another proof of existence of an eigenvalue, because again we have to use the fundamental theorem of algebra, because the annihilating polynomial will have a root by the fundamental theorem of algebra, and that will be a root of the polynomial. And the proof is quite simple, because so I am trying to prove that if lambda naught is a root of the annihilating polynomial, then it is an eigenvalue of A.
Hello, sir.
Yeah.
You said like any root of the annihilating polynomial is an eigenvalue.
Yeah.
I think it's false.
Why?
Because annihilating polynomial can have more roots. We take just identity matrix, its annihilating polynomial maybe x power n, and x power n into some x minus 1 is also an annihilating polynomial. Something like that.
No, what is the matrix? Identity matrix.
If we just take identity matrix, its characteristic polynomial will be x power n. It is an annihilating polynomial, and x power n into x minus 2 is also an annihilating polynomial. But,
Okay. I take it back. Yeah, I should say that you are right. You are right. Let me rephrase my statement. That because when I go to the proof, I would have realized my mistake, but you are quite right. Some root of the annihilating polynomial. Okay, there is one root of the annihilating polynomial, which is an eigenvalue of A. Okay, that's what I claim. All right. Is it okay?
sir.
Yeah. So when I go to the proof, actually, my mistake would have been clear. Okay, thank you. So when we go to the annihilating polynomial and factor it, so that has complex roots. So I can factor it, the annihilating polynomial, as some constant times the root z minus lambda 1. Sorry. So z minus lambda 1. These are the roots. Let me use k. Suppose it is of degree k. Or actually, yeah, so factor it. And then now if you substitute a, so the matrix polynomial, so it will be a minus lambda 1 up to a minus lambda k I. Okay. So now because I mean this is actually equal to 0 because powers of a also commute. So if we expand this, we will get 0 because that's an annihilating polynomial. So PA is 0, so this is 0. So now here is where, so this product of matrices is the 0 matrix. That means it's a singular matrix. So that means one of them must be singular. That is where I can pick up only one eigenvalue. So there must be one eigenvalue, say lambda I, such that this is singular. Because the product is the null matrix. This product is the 0 matrix because it's an annihilating polynomial. So there is one eigenvalue, one number for which it is singular, and so that must be an eigenvalue. So there is some root of the annihilating polynomial, which is also an eigenvalue of the matrix. And yeah.
ठीक है आज आए हैं आप हैं?
Okay, so that is why we have another proof of.
ऑफिस में हूँ केबिन में नहीं गया हूँ ना वो तो मीटिंग करने के लिए कल मैं गया हूँ ना
So here all the roots of the annihilating polynomial will be eigenvalues for A.
No. That was a mistake I said earlier. Not all the roots.
Okay.
One of the roots, you look at all the roots, and one of them will be an eigenvalue, at least one, because the product is singular. The product is 0.
Okay.
So one of them must be singular. That's all I can say.
Okay.
So there exists, as we had the identity matrix, there is one root of the annihilating polynomial, which is an eigenvalue of A. But this shows another proof of the existence of eigenvalue, which is quite different from the earlier.
Thank you, sir.
Yeah. Okay, then some facts about, now let us go to multiplicity and so on. So the eigenvalues, as you know, may not be distinct. So so one fact that I will not prove, but which is not difficult to prove actually, that if you take two eigenvalues lambda and mu, and these are corresponding eigenvectors, some eigenvectors, and if lambda and mu are distinct, then x and y are linearly independent. That is not difficult to prove. And also if you take several eigenvalues, distinct eigenvalues, and then take the corresponding eigenvectors, will be linearly independent. And okay, so there are, so let us talk about the multiplicities. So we talked about the eigenspace. So eigenspace is a vector space, as we saw, and that is the space of all x such that AX is lambda X. Lambda is fixed. If you want, you can call it V lambda. Then the dimension of V lambda is called a geometric multiplicity of lambda. So that is one kind of multiplicity, geometric multiplicity. And another multiplicity comes from the characteristic polynomial, that if you look at the polynomial and if you factor it. So if you look at the roots of this, so suppose it has distinct roots. Suppose lambda 1 to lambda k, and the roots will have multiplicities in the usual sense. That means if you factor it, and so sorry, I have to take the determinant. Okay, so sometimes I talk about lambda I minus a, sometimes I talk about a minus lambda I. So it depends. So let me just say that when you factor the polynomial, if this comes k1 times as a root, if lambda 1 comes k1 times, lambda 2 comes k2 times, then those are called algebraic multiplicity. So k1 is the algebraic multiplicity of lambda 1. K2 is the algebraic multiplicity of lambda. So the algebraic multiplicity is the number of times it occurs as a root of the characteristic polynomial. So that is the other kind of multiplicity. And there are lots of facts about this. Actually, I'm not planning to sort of give all the proofs because it's not possible. So I'll give some references. There are many books available, but especially on non-negative matrices also I'll mention some books. But for linear algebra, you can take standard text. And actually, I have seen one recent book by Garcia and Horn, which I'm referring, which is quite good. Some of the linear algebra books are, they emphasize the functional analytic viewpoint too much. That means they suddenly move on. For them, matrix is a linear operator only, nothing more, nothing. So they avoid even the word matrix. So I think in the beginning, you should see some books which are geared towards matrices. The undergraduate book of Rao and Bhimasankaran is also quite good. And there are books by Zhang. Problems, he has two books. One is on problems in linear algebra and one is just a linear algebra. So you can look for these on the internet and go through this. Okay, so just to take some examples, so there's a relation between the algebraic multiplicity and the geometric multiplicity, which I will not prove, that the algebraic multiplicity of lambda, of any eigenvalue of lambda, is always greater than or equal to the geometric multiplicity. I'll take this without proof. And a good example where the inequality is strict. So if you take a symmetric matrix, we will talk about a symmetric matrix, all the eigenvalues happen to be real. And so real symmetric matrix, all the eigenvalues are real. And there the algebraic and geometric multiplicities are equal. Or if you take a diagonal matrix which is symmetric, then also they are equal. A good example where they are not equal is something like what is called a Jordan block. Something like this. Or just to make it clear, let me put some number here. So this matrix has one eigenvalue only, that is 4. Because if you look at the characteristic polynomial, you get determinant of lambda minus 4 squared. So there's only one eigenvalue. And because it is lambda minus 4 squared, It occurs twice. So the algebraic multiplicity of 4 is 2. But if you look at the eigenvectors, so that means that will give you the equation x, y. So you get two equations. One is 4x plus y is equal to 4x, and one is 4y is equal to 4y. So this equation is meaningless. It always holds. And the first equation only says that y is equal to 0. So if you take any vector of the form x0, that is an eigenvector, and that's a vector space of dimension 1. So the geometric multiplicity is 1. So the algebraic multiplicity is strictly greater than the geometric multiplicity. Okay, so actually I should state the general theorem here about. So we are interested in reducing the matrix to a simpler form through a process of what is called diagonalization. So if you take a matrix A, and if you take a matrix of the form S, A, S inverse, where S is a non-singular matrix, then they are called similar matrices. And similar matrices have the same characteristic polynomial and the same eigenvalues. And so we will try to reduce a matrix to a simpler form by multiplying on the one side by S and on the other side by S inverse. And that's called a canonical form. And one of the very powerful canonical forms is the Jordan canonical form. And I'll state the Jordan canonical form, sort of describe the Jordan canonical form without proof. So Jordan canonical form, actually Jordan canonical form reveals quite a bit about the eigenvalues and eigenvectors. So if you have a first course in linear algebra, typically it should end with the Jordan canonical form. So given a square matrix, so now I'm talking of a square complex matrix, you can find a non-singular matrix S such that it has the following structure, that it's a block diagonal matrix. That means there are blocks and so on. And each one of them is called a Jordan block. So what is a Jordan block? A Jordan block is a matrix of the form, there is some number on the diagonal and 1 on the super diagonal and everything else is 0. So that is called a Jordan block. And the interesting thing about this matrix, the Jordan block, if you look at this matrix here and look at its eigenvalues and eigenvectors, just like we did the 2 by 2 matrix 0, 1, 0, 0, very similar to that, you will see that this matrix has only one eigenvalue, that is mu. And the algebraic multiplicity of mu is the order of this block. That is obvious because if the order of this block is m by m, then mu will come m times. So algebraic multiplicity is m. Now, similar to what we did earlier, if you look at the characteristic equation, eigenvalue eigenvector equation, then you will see that mu has only one linearly independent eigenvector. Because those equations become very simple and it's very easy to show that there's only one independent eigenvector. And so mu has algebraic multiplicity 1 and geometric multiplicity, algebraic multiplicity m and geometric multiplicity 1. Okay. So for any eigenvalue, if mu is an eigenvalue with algebraic multiplicity, say small p, and geometric multiplicity, small q, then there will be small q blocks all having all of this form. That means they will have mu on the diagonal, 1 on the super diagonal. Their sizes will be different, of course. And the total order of these blocks will be P. The J1, J2, JQ, so they all correspond to one eigenvalue, namely mu. For every eigenvalue, there are blocks. And if an eigenvalue has geometric multiplicity Q, then there are Q blocks for that eigenvalue. And the total size of those blocks adds up to the algebraic multiplicity. And that is the Jordan canonical form. And it is also, there's a uniqueness that it is unique up to permutation of rows and columns and so on. Okay, so that reveals quite a bit about the, in fact, whatever you want to know, the elementary properties of eigenvalues and eigenvectors, they can be deduced from the Jordan canonical form. We will not need the Jordan canonical form statement much, but this is a very fundamental fact. I think I want to just give one example or one sort of illustration that, so there is one property of eigenvalues and eigenvectors, that if a matrix A has eigenvalues lambda 1, lambda n by n matrix, then A squared has eigenvalues lambda 1 squared, lambda n squared. Now, what is the proof of that? So let me just tell you that usually the way this is proved, even in classroom by teachers also, is that they will say that suppose X is an eigenvector for lambda, then Ax is equal to lambda x for some x, and then we multiply by A, so we get A squared x is equal to lambda Ax, but Ax is equal to lambda x, so you get lambda squared x. So from this equation, lambda squared is an eigenvalue of A squared, and they claim that the proof is complete. But if you look at it carefully, the proof is not complete. There's a gap in this proof because we have not talked about the multiplicity. That means we have not talked about the converse. Very simply, if I say that suppose A has eigenvalues 1, 1, 3, 3, 3, and I claim that A squared has eigenvalues 1, 1, 1, 9, 9. Then you have not contradicted that. Because what you have shown is that if A has eigenvalue lambda, then A squared has eigenvalue lambda squared. That's all you have shown. And it is satisfied in this example. A has eigenvalue 1, A squared also has eigenvalue 1. A has eigenvalue 3, A squared also has eigenvalue, A squared has eigenvalue 3 squared. But this doesn't happen. As we know, this doesn't happen. In fact, it has to be 1, 1, 9, 9, 9. And that we have not proved. And it turns out, and this is not told to the students at all. The fact is that the proof is not very easy here. If you want to prove it completely, so there is another fact that if A has eigenvalues lambda 1 up to lambda n, then any polynomial in A, you take any polynomial in A, PA, and that has eigenvalues P lambda 1 up to P lambda n. And this also requires a proof, and essentially that whole proof is required in proving this statement also. Okay. So there is a proof available, I think, in the problems. This is one of the problems in your problem sheet. So in the, some of you can try to prove it by some way, but it will maybe discussed if there is time in the problem sheet. Otherwise, you can see some reference. But my comment here is that if you use the Jordan canonical form, then these kinds of statements become immediate. because if you look at the Jordan form of canonical form of A, and then if you look at the Jordan canonical form of A squared, then let me not say anything more from the Jordan. If you assume the Jordan canonical form, then this statement itself becomes very easy to prove. So it's a very powerful result. And when you come to some special class, like if you come to symmetric matrices, so I made a comment earlier that if you take a symmetric matrix, so let me now come to real matrices for a while. So, or actually from now on, I'll mostly talk about real matrices. So if A is real symmetric, so sometimes I'll just say symmetric, which means real symmetric. Then eigenvalues of A are real. They cannot be complex. And again, the usual proof given is through eigenvectors. So, and that proof is correct. There's no problem about that. But the only problem is that suppose lambda is an eigenvalue, then A is real. We want to show that lambda is real. X may not be real. So that means essentially you have to enter the area of complex matrices, because unless you go to complex matrices, you are not guaranteed existence of lambda and X. But once you do that, then the proof is there. You have to pre-multiply by X conjugate and then do something. So that's okay. But another comment is that suppose you don't know complex numbers at all. You are in the world of real matrices, real numbers only. How much can you do? There is no problem about defining determinants. You don't need complex numbers. Then there is no problem of defining eigenvalues, because I can use the determinant. I can say that lambda is an eigenvalue, the determinant is 0. Lambda I minus A is 0. And A symmetric, so definition of symmetric is just high school stuff. That means A symmetric means A transpose is equal to A. And then, so it's a kind of a combinatorial condition. It's not an algebraic condition, just combinatorial condition. That pattern of A and A transpose, it has something to do with that. And with that information, then determinant lambda I minus A you expand as a polynomial. And then you are saying that the roots are real. That means they exist, because I don't know complex numbers. I'm not saying that the roots are real. You have to show that they exist. Okay, so I don't see why you have to go to complex numbers here, because everything up to here is kind of high school only, because defining determinant, defining symmetry, reality of roots. So you have to go to the entire vector space theory to show that the roots are real. So you might be wondering, isn't there an easier proof? Easier in the sense of not mathematically easier, but conceptually easier. That means doesn't use higher mathematics, doesn't use vector space theory. And if you search enough, there are such proofs available, but I won't talk about that because they use induction. So they use induction. Yes, any question? Okay, so they use induction and so on. But this is just a remark that. So I think linear algebra, the thing to keep in mind in linear algebra, that there's a certain topic that you are looking at. And when you are trying to solve something, you have to attack it from all sides. So whatever you know, all the tools that you know, they have to be employed, and then you can solve the problem. if you don't use some of the tools, I'm not saying that it's impossible. Sometimes it's impossible, but sometimes it's very difficult. And so it is, the crucial thing is to know how you can use the combination of all the tools. And maybe I'll give more examples of this later on. But for a real symmetric matrix, the eigenvalues are real. Just think of this, how to prove it without using vector spaces. That means you should not use because the statement doesn't need vector spaces. That is why it only needs determinant and polynomials. Okay, so now for a real symmetric matrix or a symmetric matrix, the Jordan canonical, yeah.
Sir, this thing, real symmetric matrix, eigenvalues are real.
Yeah.
This is like a sufficient condition for when for a matrix all the eigenvalues will be real. Is there any necessary condition when all the eigenvalues can be real?
No. Unfortunately, there is no there is no such theorem that that the eigenvalues are real if and only if. No. But you can say that. Yeah. So no, there is no such condition because all kinds of matrices can have real eigenvalues because of many different reasons, and there is no such general theorem, unfortunately. Okay, there is no such theorem. So symmetry of the matrix is just very simple condition, but symmetry is not at all necessary. You can have a very complicated matrix where this is real and there is some very complicated thing sitting here and this is 0. Then the eigenvalues will be real because there will be the diagonal entries. This is the upper triangular matrix. And
It should be similar to such a diagonal matrix where the diagonal entries are all real.
So you are saying it should be similar?
If it is similar, then to such a diagonal matrix where all the diagonal
If it is similar to such a matrix, then also it will have a real eigenvalue. But still, I am not saying it is necessary and sufficient.
No, it's just sufficient.
Yeah. So there is no necessary and sufficient condition. Okay, so what was the Jordan canonical form? It takes a simpler form when we come to a real symmetric matrix, and that is called a spectral theorem. And spectral theorem says that if you have a symmetric matrix, and this can be done even for a Hermitian matrix, complex Hermitian matrix, but let me not go into that. So if you have a symmetric matrix, then there is an orthogonal matrix. Orthogonal means P transpose P is identity. And again, in complex case, it will be unitary, but let's not talk about that. I'm talking of symmetric, real symmetry. So there's an orthogonal matrix P such that PAP transpose is diagonal matrix. And those diagonal elements are then the eigenvalues because A and P dash are similar. P dash is P inverse if P is orthogonal. So that is the spectral theorem. And that is extended to operators, and that is the basic theorem in functional analysis and so on. And there is the corresponding eigen decomposition. So when we talk of positive definite matrices, then this plays a very important role. But for Perron-Frobenius theory, we will not go much into symmetry because symmetric matrices is a whole theory which is more to do with the spectral theorem. But whatever you want to prove for symmetric eigenvalues of symmetric matrix, you can usually prove using spectral theorem. Like I said that if A has eigenvalue lambda 1 up to lambda n, then A squared has eigenvalue lambda 1 squared. That becomes immediate from the spectral theorem because P A squared P dash, if you just evaluate. So that becomes very simple. So all these things become very easy when we go to a symmetric matrix. That just the spectral theorem. Not everything is possible, but most of the things are possible using the spectral theorem. Okay, so now let me just go to Perron's theorem and at least introduce. So I want to give essentially 2 proofs out of those several proofs. And those I will give more or less completely. And one of the proofs, which was due to Blackwell and others. So they use a fixed point theorem. So I want to first talk about that. And they use a fixed point theorem. A fixed point theorem means anything which says that a function has a fixed point. The x says that fx is equal to x. So what are the existence conditions? For example, the usual mean value theorem. Like if you take a function from 0, 1 to 0, 1, then it will cut the diagonal. So this is some function, continuous function, of course. And then if I take the diagonal, it will cut the graph at some point, and so it will have a fixed point. This is a fixed point because it will satisfy fx is equal to x. And there is a more general theorem called a Brouwer's. You might have heard of this in topology. Brouwer's fixed point theorem. Fixed point theorem, which says that if you take the disk, the unit disk in Rn, so you can say that all x, said that norm of x, the usual Euclidean norm, is less than or equal to 1. And so in 2 dimensions, it is just the disk. And suppose you have a function. So let me call this as dn. Of course, there's a more general version. I'm stating a special case. If you have a function from dn to dn, which is continuous, then f has a fixed point. fx is equal to x for some x. You might be wondering what this has to do with Penrose's theorem, but very soon you will see that it's a very natural technique. And Brouwer's fixed point theorem has many applications in fields like economics or game theory or this computational mathematics. And there are so Brouwer's fixed point theorem is true also for convex set. That means I don't have to use a disk. I can take something like a triangle and take a function. In fact, it need not even be convex, but then you have to talk about it's homeomorphic to a disk and so on. So then also it is true. But let me just give you as a small exercise that these are simple statements, so simple exercises. Why continuity is required? If you remove continuity, it is no longer true. And also if you remove convexity, what will fail? So you can think of those two things. Okay, so later I might give one combinatorial proof of Brouwer's fixed point theorem later on if there is time. But now let me quickly come back to a positive matrix. So A is n by n. Let me use this notation for entry-wise positive. And let us use this set Sn, which is a set of all vectors in Rn. These are probability vectors. That means x is entry-wise non-negative and summation xi is equal to 1. And I will define a function f from Sn to itself. What is the function? Function is very easy. You take a vector x in Sn, then go to y equal to ax. Obviously, y cannot be 0, the null vector, because x is at least non-negative. X may have zeros, but a is positive. So ax is definitely not 0 vector. So y is definitely not 0 vector. So then I will go to another vector, or actually let me just here itself, because y may not be a probability vector. The components may not add up to 1. So I divide this, I normalize it. That means I divide it by the sum of the elements. Just normalize it. Then it becomes a probability vector. Then it becomes, and I can do this because y is not the zero vector. So y is also in Sn. So I have a function f from Sn to Sn, which is obviously continuous because all these operations are continuous, ax and so on. So it has, by Brouwer's fixed point theorem, it has a fixed point. That means f of x naught is equal to x naught for some x naught, and that means if you write it in terms of y, that means ax naught divided by some number, let me just call it alpha, is equal to x naught, and so ax naught is equal to alpha x naught. So we have this alpha is nothing but this quantity evaluated for x naught. So we have shown the existence of, so alpha is definitely positive, and x naught is also non-negative at least. And so we have shown the existence of a positive eigenvalue. And we have also shown that there's a corresponding non-negative eigenvector. And so by Brouwer's fixed point theorem, the proof is immediate. But the other assertions of Penrose theorem, they require more work, and which we will do next time. So I suggest, so let me end by giving you the basic references. So for non-negative matrices, you can, I'll just take 2 minutes. So one is, there's a book which is suitable for this level, but I'm not very sure whether the PDF is available. This is by Mink, because this is a very easy book to follow, non-negative matrices. If you can download this book, it's very good. Otherwise, the earlier book is Berman and Plemons. That also the PDF may not, these are old books. Berman and Plemons, similar title. And there are, so I'm just mentioning non-negative matrices. And I have a book with Raghavan. Some parts of that, so myself and Raghavan, that you can find on the internet, Cambridge University Press. So at least the first chapter will be on, all the book has to do with non-negative matrices. The whole book has to do with non-negative matrices. So for your later references, this may be a good start. Okay, so some problems are posted, so you can try those problems. Actually, so this area you will have to put in a lot of work if you want to sort of get the, understand it really well, but at least the basic points, I hope that you will get through this series. Okay, so unless there are questions, you can ask, otherwise I'll conclude now. And tomorrow I'll talk about the other assertions of Penrose theorem and try to give the other proof as much as time permits. Okay, so I think we'll stop with that. Yeah, what is the